Yeah, thank you everyone. Thank you for inviting me for this talk. Today I'll talk about graph-based processing of big images. So this workshop is more like theory to practice, and this is like almost 90% practice and 10% theory. But it will give very good motivation on why should we be building such linear solver, right? Because today, throughout the course of this workshop, you hear about a lot of like work done, but there isn't much about talk about the demand for such solvers. And today we're going to go through detailed motivation for image processing. Okay, so a brief introduction. Most of you might not have known me. Currently I'm a member of technical staff at the Signal Processing Lab at a defense science organization in Singapore. So we are like the army research or naval research equivalent in Singapore. So we work for the military. And my personal interest is in compressive sensing for imaging radar, electro-optical satellites exploitation, and how to process image quickly. And previously I was from CMU. I worked with Gary and Richard, the previous speaker. And the talk will be structured into three portions. One is what is the big image challenge, and how can we reformulate this image processing task as graph-based problems. And the last one is talk about practical approaches and challenges to using linear solvers in doing this image processing task. So now it has the word big, right? So the thing that comes to most of mind is like big data. This is like the buzzword today. So we all know when you talk about big data, the things we think about is like Google, Amazon, and Facebook. And if you Google, right, the word big data, you realize that it's represented by mostly blue pictures. I do not really know why, but this is the reality. But what is big the Okay, so the biggest difference between big image and big data is in big data, it's highly unstructured. You're always given a bunch of data points, and your goal is to find the hidden communities, the structure underlying this, or the genetic model that's creating this big data. And there's a lot of advance in the recent years, such as deep belief networks, manifold learning. However, for images and signal processing, the data we're looking at is already highly structured. The structure is because the way we observe the world and the way the imaging sensors are created. So how can we exploit this underlying structure for efficient computation? And you probably would guess that the structure is a graph, right? In fact, it's a very nice graph. It's like a grid graph. So these are the sensors we have today. So they are big in terms of scale and volume. For example, the WorldView 3 satellites, which was launched this year, August, and it's getting ubiquitous and fast like your GoPro cameras. And the last one is on high dimension. We're looking at like light field imaging, hyperspectral imaging. So the image data will become high dimension in the near future. And the goal today, what is known as efficient computation in image processing, will be to process 2 GB of images under 5 minutes. So I did not pull these numbers off. If you go and read like the US DARPA paper, this is usually the goal that they will state, because this translates to some kind of kill chain if you're interested. There's a time required to like kill someone. Okay. So this is a current state of the art by the US program. So they have this Gorgon Stare 2, which is comprising of 368 cameras, and it senses 1.8 billion pixels at 12 frames per second. So that translates to about 50 gigabytes per second. And this is already larger than what your gigabit Ethernet can process. So how do they actually get about doing this? So today, what people do is they actually take big images, they chop them up, and they parallel process them without having any notion of what is the overview of the image itself. So for example, this is a Google map image, right? And you can see that clearly there are seams from the part where they actually partition the image, and they don't actually bother like trying to glue them up, because doing that is quite hard. So what we want to do is to actually process the images as an entire data cube in an efficient manner. So by doing that, it gives you new means of new novel ways of doing image processing. So we're going to do a comparison from Hyperlapse. It's a Microsoft SIGGRAPH paper in this year. The left side is a single frame rendering, the right side is a multi-frame rendering. So basically the right side will be rendered based on the entire data cube itself. As you can see, if you have the entire data cube, you can actually compensate for missing pixels way better than any kind of electro-optic stabilization software you have today. And this is built upon a few techniques. They use Markov random field and Poisson blending technologies. Okay, so that's the big image challenge itself. The big image challenge is to process image dataset globally in an efficient manner. Okay, so we'll get that. Okay, so now let's before we can talk about image processing, let's talk about signal processing. So maybe not everyone is familiar with signal processing, so I just added this bunch of like 101 slides. So if it's too boring, and then I apologize. But anyway, so the goal of every single signal processing task is, given a sampled signal, it's usually convolved with a transfer function and then added with some additive noise. And the goal is always to recover the signal itself. So we have like noisy linear, which is a very famous picture in computer vision, and the goal is always to try to denoise linear. And if I give you this as linear and ask you, do you believe this is the original linear? Answer will be yes. But why would you say yes? Because everyone has a prior notion of what the structure of the signal should be. So we have an inherent idea of what natural signal should be. So if you, and all of this EC actually has, all of signal processing has more or less like 3 flavors of assumption. So the first one is if you believe your signal is band limited, then you have your traditional Shannon-Nyquist processing. So almost all of electrical engineering is based on that assumption. So we have filter designs, everything is based on the Shannon-Nyquist sampling rate. It's all based on this band limited assumption. So band limited is that your signal is compact and has finite support. So that's the main assumption. But if you believe your signal has finite support but sparse, then in 2006, there's 2 groups of people, Candice, Robert, and Tao, and Don Ho, independently discovered this notion of compressive sensing. And this was already mentioned by a few speakers in this workshop itself. Like, compressive sensing is another way to view signal processing, where the signal is sparse. And lastly, if you believe there's correlation in your signal itself, then we're going to have a graph-based approach we will talk about in this talk. So before that, we should have some remarks on compressive sensing, since it's like the really new topic and it uses a lot of L1 solvers, and this is potentially another area which the solvers technology can go over to. So the main assumption is that the signal itself is sparse and there has some minimum separation between the signals. So I'm sure you have heard this theme a few times already. Maybe like even the topic modeling, they tend to use this as well. So having these 2 assumptions are very powerful because it allows you to reduce the number of samples that you're required to reconstruct the signal. So one of this very famous example is the 1 pixel camera by Justin Romberg, Kelly, and from the University of Rice, where they just sense the whole world using 1 single photodiode, and they can reconstruct as good as a normal 2D, 2-dimensional array cameras. However, there's one major caveat, is that if you are going to higher and higher resolutions, you actually cannot beat the true Shannon-Nyquist bounds. So what is this? Is this due to a phenomenon as coherence? So if you're approaching to the physical limit of the sensor, there is this phenomenon as coherence, which forbids you from actually beating the Shannon-Nyquist rate. So what it means is that at the end of the day, right, if you really want to have high resolution images, you're pretty much stuck at processing all the pixels again. So yeah, so which gives some motivation on why should we carry on work in all the large solvers. Okay, so we're going to talk through how do you transform image processing problems into graph-based problems. So we start off with one very famous, pretty famous function known as the Mumford Shah. So it's given an image and a model J and some boundary D. So the function is written in this form. So if there's a square difference between the model, the image and the model, and this is actually correct. It's actually the square of the gradients, and the last one is the connected components, the boundary of the model itself. So it's essentially there are 3 terms, right? It's fidelity, smoothness, and components. So some combination of this actually produce a different kind of image processing algorithm. So if you take the one with the connected component, you get the Chan-Versal segmentation algorithm. Then the one we're going to talk about today is actually the TV variational denoising. So the RF92 model, or Rudin, Osher, Fatemi model, is given a noisy image S. Our goal is to recover X, right? And the functional is, we have seen a few times already this function appearing. So it's the square of the 2 norm of the difference and the absolute, or the 1 norm of the recovered pixel difference. So what this translates to is actually you're applying a Gaussian noise prior, and you're having a prior of that the edge have a Laplacian distribution. So this came actually naturally from the Mumford Shah functional. So this is just some interesting. It was actually designed for guiding. RF92 was actually designed to guide weapons. So in case you don't know that, most of the image processing was designed to drop bombs. So the thing is that the TV is we already know this function as it's been mentioned a few times in the talk, and it belongs to a class of what is known as bounded variational problems. So interestingly, a lot of the image processing task has a bounded variational functional. The reason being because the convergence for this set of this family of functionals is already very well known and well studied. So if you can write this, you will notice that like segmentation, like level set segmentation, stuff like that, they all have a bounded variational function somewhere to ensure convergence. So the TV, it was designed, RF92 was designed in 92, right?
Excuse me. In 2001, I had a paper published in JSCM on Markov random-fate and segmentation that showed that if these functions are convex, there is an algorithm which is the fastest possible. So, for instance, with the image that you showed 3 slides ago, the function that you have there is solved as a minimum cut on a graph.
Right.
And if the deviation is any convex function, is solved as a parametric cut on the graph, and the running time is the best possible, you can't improve it. So I don't see how you can relate to this. All of these are later papers, and the result there dominates all of them.
No, this one is not saying that these are fast runtime. What this slide is trying to say is movement towards from interior point methods to using the linear systems itself. So this slide is not talking about, this is not a comparison of runtime, right?
But these are TV algorithms, and this one is also a TV algorithm.
Yeah, I agree, but this was designed specifically for TV denoising. So I think yours solve a larger class of problems.
The difference is the isometric or anisometric. Markov random field is anisometric. Total variation is isometric because the image is 2D. The L1 is L21. Usually total variation is L21. Markov random field is L11.
No, it doesn't have to be.
I mean,
it can be any complex function.
No, I agree with you. Like, the point of this slide is not saying the methods to solve the TVD, but these algorithms were specifically designed to solve the TVD problem. I would believe you that your algorithms solve a larger set of problems.
But it's also the running time is best possible.
No. This whole area is not talking about running time. It's more about what was the, because this set of slides, right? We're not going to say that this is the fastest running time, but it's more like what was the movement from trying to solve these problems. It's more like the intuition rather than the running time comparison.
Yes, I know that the graphical is the best method for Markov random field.
So I guess the question is, what was the motivation for this movement?
Right.
That's, I mean, I guess that's the question.
So the motivation, right, is that they started. If you look at the timestamps, right, they started noticing the linear solver sites. So a lot of these were actually just borrowing ideas from solving linear systems. And this was actually, so instead of solving the original TVD problem by using, yes?
Is the difference maybe solving exactly the problem versus solving approximately the problem?
But why would solving approximately the problem be superior to solving exactly the problem?
Because you can do it much faster.
But you can't.
Approximately. Approximately, maybe, yes.
What does it mean?
The max flow, for example, you can do it in linear time almost. Approximately.
But I'm using max flow.
Yes, but you do the exact. So it is an approximate version of the problem.
If you're using max flow, it's unclear how it can be the optimal, how you can claim it's an optimal running time.
Well, I show it that it's an optimal running time because it's a generalization. I use actually min cut, not max flow. It's not exactly the same. And I show that.
Yeah, but if you want to solve min cut, why not? Why, you know, you can do other things besides. I mean, you can do other things. You can use linear systems to solve min cut.
No, but
I'm just mystified by why an algorithm that is superior in every way to these algorithms is not even mentioned as a possibility.
Oh, okay, I'll look. We can take this. I'll ask you. Maybe we can update a future version of the slides. But anyway, this two, yeah, it was correctly pointed out. They were actually approximate methods. They don't actually solve it exactly. So then we have the entire on the other side of the camp is because there was a lot of development in the linear solver side as well, right? So, I mean, most of you should be familiar with this. So, the point being is that the computer vision community started noticing some of the ideas that were coming from the theoretical communities on solving linear systems. So, for example, like Brinkman iteration, right? It was just a pure copy of coordinate fixing. They just like more or less like transplanted some ideas to solve matrices by fixing coordinates. Okay. So now we come to the Laplacian paradigm itself. So we're going to talk about, I think it's been mentioned a few times around in this talk. So the idea is to rewrite a lot of the problems that you have currently as graph-based problems, and then we just take the linears, we take a linear system solver and just throw at it, and that's it. We're done. So you can generate a lot of paper by just showing new runtimes that if you have a good linear system solver, you naturally get a lot of good runtimes for the other algorithms. So the thing is that graphs are actually discrete. No, sorry. The continuous signals, right, are actually discrete objects, right? It's simply because that the physical senses are discrete. So the way you sense them results you to have a discrete structure, and this discrete structures are actually vertices of a graph. And there's actually a lot of other papers talking about what kind of losses do you get when you do this discrete to continuous approximation. So I think Ben Reck has a bunch of papers, it's not here today, but on this phenomenon itself, on the errors and how do you actually do an exact reconstruction of the continuous signal. The graph-based approach we are talking about today is that it's given some vertices that represents a noisy signal, we want to recover the signals which represents the denoise signal, and then we have a bunch of like edges that runs around, and at the end of the day we want to minimize some function over the graph. Okay, so let's take the TV model and see how it's being rewritten as a graph Laplacian problem. So let B be the boundary operator, so between the vertex to the edge. So if you put in a vertex, it spits you on edge. And if you want to solve that function on top, right, so effectively it's saying that we take the boundary on the x itself, that means x is the solutions I want to get, and it has to be small because I want the neighbors to be small, so I put 0 for now. And then the edges that runs from x to s, this term has to be small too, so it gets a boundary of 0. But you notice that something is wrong here, right, because I basically just wipe away the norms to jump to the next step. So I kind of like drop the L1 penalty, and I promise you I'll put in a W such that this weighted vertices will get you the right answers. We'll see why later. And finally, we hit it by transpose to form the Laplacian. So this gives you some form of quadratic form, and this is the final form that we get. So the final form is we have here Laplacian, Laplacian which representing a grid graph plus the identity, and we will solve this linear system. Right? So everyone clear so far? So intuitively, the picture will be you have a grid graph which represents your solution space, and you have for every vertex there is one edge that runs into the constraint space, and then we want to solve for this functional over this graph. So, and it's not exactly right because the fact that I wiped away the L1 and try to use an L2 to solve it means there is some gap somewhere. So anyway, this trick is pretty typical if you look at compressive sensing literature and weighted least squares. So the reason why there was a W, right? So we wanted to reweight it every cycle such that the L2 will approximate the L1. So suppose at convergence, that means you already had the right weights at the end of when the algorithm converges, then what would it be, right? So this is the 2 and this is the 1. You go through the math is that if at convergence we had the right solutions, then the weight had to be satisfying this, right? It's just like just 1 over the square root of the excess weights. So what is the trick here? The trick here is to use what we call the group least square solution. So again, we know is not necessarily the fastest. Really. There are a lot of other solutions. Maybe split Brickman is way faster than this algorithm. But what is Q?
Huh? Are you talking specifically about the problem on top of? Can you back up a couple of slides? What you're discussing, this one. Are you talking about the problem on the top of this page?
Yeah, this one. Only this one.
Okay.
Yeah.
So this one is just one minimum cut.
No, I agree. We know there are like a lot.
So there was a lot of discussion here in this semester that you can solve maximum flow and maybe minimum cut with the Laplacian system. So this is now something different.
No.
Don't you want the W inside the grid? I mean, it's the weights of the edges of the grid graph.
You can put, you can imagine it as W can absorb anywhere, right? Doesn't really matter. It just means the W per vertex. No, this one is not saying that. This is what I'm trying to say is that we can use linear solvers in this formulation to solve this class of problem. So as to why do we want to do that, the motivation will be later down. We show that once we start writing all the problems as graph-based problems, we can start mix and matching them together. And because you have a linear solver, right, you can actually control the degree of solution or the degree of progress you have. As opposed if you something like split Brickman, which gives you the exact answer at the end. So we will show why you want to do that later. So the right this method converges. It was proven. It was given in a paper that we wrote in 2012 using electrical flows. So anyway, we don't claim we have the fastest way of doing it, but we're just saying that doing in this form, right, you have some neat applications we will show later. Okay, so then the other set of equations, right, which we already mentioned, is like Poisson image blending. So it's a very simple idea of that you put a Poisson, you put a gradient field over an image, and then you have some Dirichlet boundary. You just solve the system, right? This is formulated in 03, and I'm pretty sure it was known way before that. But with that technology, you can do image transfer, similar. Like you can place polar bears and naval fleets in a pool, and this style of this style of doing graphics as graph problem in the recent year in 2013 to 2014, right? You see there's a lot of papers coming out where they want to talk about solving graphical systems, graphs that mimics a certain computer graphics problem. So I claim that actually all of your traditional image processing actually falls into two classes of problems. They are either zero order constraint on the image itself. If you do that, you get zero order constraint means that we fix the vertex values, right? So with that, you actually get convolution filters and a bunch of filters. The way we usually think of it is like, what is a mean convolution filter over an image? So it's just basically you have like you want to solve a graph where the vertices are all connected to the constraints, right? The image you're given, but there are no edges that are running between the solutions. And you just solve for the 2 norm, and then magically you get convolution filters. And there's a bunch of papers that shows a reduction of a large class of filters into this form. The next one, if you have up to first order constraint, meaning that you want to constrain the differences between pixel values, in addition to the difference between the constraints you have initially, you will get like TV denoising, Poisson edge blending, and so on and so forth. And in fact, we produce this bunch of results, everything using the same solver base code. And there's nothing much you need to change actually. You just need to write you just need to generate the grid graph and just write the function that you want to solve, and the solver takes care of it. So why do you want to actually do this style of processing? So firstly is to take advantage of linear solvers. So we are trying to bring together all the different kind of image processing problems into one unified framework where I can just throw the linear solver once I have a graph Laplacian. And the next one is to leverage on some new graph technologies developed by the big data community. So this one is more like, there are some new technologies, like MapReduce is actually a very old technology in big data. But we are trying to like steal some of the new technologies that are slowly developing in the big data community. So this one is from my own experience developing some of these technologies. That this gives you a good sense of like what technology, what system approach you should take given the graph, the problem size. So anything less than 10 gigabyte, right? We discovered that if you just use like the GPU accelerated solutions, they are pretty competitive to most of our sparsifiers you have right now. And they do really silly stuff like conjugate gradient, and it works. The reason why is because the GPU has a lot of cores, so you're actually taking like almost an order of magnitude of processing cores into your problem. And if you have something within 10 gigabyte to 1 terabyte, you best use an in-memory solution with bulk synchronous. So they do not want to pay the communication overhead between the computation nodes. The last one is anything greater than 1 terabyte, you have to gun for a asynchronous disk-based solution. So if any of you developing like really, really large solvers, these are the like sort of like the steps that you want to take. The reason why it's 1 terabyte, it's typically that's what you can get off the shelf these days. About board with four CPUs, then maybe like 16 racks, and each of them you put in a few.
So I see. So you're saying that GPU-based things can compete for these sizes?
Yeah, these sizes they can.
But in principle, many of the basic operations inside Sims they can be done. It is matrix multiplication. Does that?
Correct.
Can that be used in?
So that's the next slide. So okay. If you want to use matrix mult, you must use a GPU somewhere to be competitive these days. Okay. So even though we're developing like theoretical solvers, right? Once you implement in code, like any kind of like sequential CPU will lose the GPU like straight up for matrix mult.
Is that also true for sparse graphs, that you can have good implementations on GPU?
Yes.
Because I talked to other people who told me no, but I believe you. Yes.
Yes. Sparse graph you can do very fast on GPUs too.
Yeah. Okay.
But because that's given a good ordering of the graph, you can do it.
Yeah. Okay.
So and this was actually surprising because the 2004 Hyperlapse paper you saw just now at the start, even though they have a really large system, right, they're still using conjugate gradients, and they run to like run times of like a few hours to solve the cube itself, which we know can be definitely done a lot faster. The last one is about, this one was actually mentioned by the IBM group. They were doing the, what's that called? The Skylab group. So one of the problems that we usually don't talk about in this community is that even though we want to solve the system, right, the system itself needs data, and data has to be pre-positioned beforehand. Meaning is like you cannot assume that if you're distributed over a few computers, right, that every machine has the global view of all the data. Does that make sense? Because what happens is that most of the time, 80% of your overhead is actually doing data copying. So all the like MapReduce stuff, right, even though it takes like maybe a few minutes to compute, but you spend like 1 hour copying all the data, the 1 terabyte of data across the different machines. So it's best that if you have, if you write solver code, right, and it does like at every parallel level, there's some means to bring the data locally and not require a off-machine query. And that will like burn away all your runtime quickly. So now the idea of why I want to use graph-based techniques is because if you have, now once you reformulate like TV denoising, spectral segmentation, Poisson blending as graph problems, right, you can see they naturally fall into the same form, and then you can use one data structure, which is your graph Laplacian, many times over and over to solve different problems. not only that, you can just throw a bunch of like Lagrange multipliers, and that controls the different rate of the different algorithms you're using. And you have a solver, right? It allows you to control the degree of solving the problem itself. So why is this useful? So first one is like we talk about spectral segmentation. This was some work with one of Gary's students years back. So the goal is to like try to segment cells inside, I think it was a lung tissue or something. Try to get these cells out. But we know, we've seen already a few times, like spectral segmentation don't really tend to do well in this kind of setup. Right. So what we did was that we kind of like tricked the spectral segmentation algorithm. We just throw in the TVD norm at the side, and that guides the spectral segmentation algorithm to get the right segmentation. And this can be done because we wrote that as a graph problem, right? And if you do it in the traditional sense, you have to like denoise first, then you segment. But in our case, we could like denoise as you segment because it was formulated in the same framework. So that helps to do better segmentation.
Picture on the right.
This is if you just do TVD denoise, this is what you get. Yeah. Okay, the next application is on. It's not my favorite.
I didn't understand. This is some kind of regularization
Yeah.
during the solution process.
Correct.
But I didn't understand what was the advantage of looking at it this way? I mean, just because you can keep you can solve the system while you regularize the whole time.
Yeah. So right now you have a grid, right? You want to have a cut that runs across, but every time you try to make a cut, then you can run one cycle of denoising by trying to reduce the edge jumps. So you simultaneously can do both algorithms in one go, and that allows you to. And you just put in some Lagrange multiplier and control how much of which algorithm appears in the final solution. Then the next one is this is like camouflage detection. So this was a picture by some US company that claimed they have like some optical stealth technology. So well, actually, if you compute this picture really it's a bit hard to understand. But what happens is that when you are trying to solve the TV denoising, if you control the step sizes, you can actually find the jumps you can find different scales of jumps, right? So you can see, right, at this area here, there's like 2 patches of variation and there's a small cut in between. But basically, the thing is that you can control how fast your linear solver is moving. And that actually gives you some new insights of what's going on in the image. And that allows you to actually detect the break. There's a very, very small break that's going on in a texture. And that gives you this ability to detect camouflage. Next one is shadow retrieval. So this one is dark.
Isn't this more impressive if the guy is not holding open?
But the other end.
So it detects the other end as well.
I know, but I mean, yeah, it's more impressive if the guy is not holding it open, right?
Yeah.
Can you do this? That's
No, it can be done. So if you actually retrieve the solution, you can actually see the person's body. The person's like lying in this direction. Yeah. If you analyze like if you analyze this, which that would be another computer vision talk on how do you detect that. But you can actually see the person's torso inside. So we can talk about how this actually works later. So the next one is on shadow retrieval. So in satellite imaging, right, so the tall building tends to cast shadows and then blocks it. So there is actually some means to recover this. So if you do your favorite Adobe, you just throw like some of the latest enhancement to it. They don't really get very good results. Right? You don't have enough information to see. No, there is enough information, but just that traditional signal processing that does some kind of local base doesn't actually give you that good result. So, well, you might not believe that this is actually better, but you can actually see a bit more detail, and this is done using both TVD and the +1 image itself. And the reason why we don't have some slight halo right now is because this is a single channel image. So the actual technology that we developed uses multispectral data that allows you to see better into the shadow. But again, we can do this is because we combine a few graph problems and put them together. And yeah, you can actually see you can't see there are more objects here. But this is a much higher resolution picture. You have to zoom in to see. Okay, so enhancement. And this is actually the main motivation for my line of work, is that these images are really big. So a satellite image typically is about, this one is really small, but the typical one is about 1 gigabyte every. So we want something that we have to be able to process everything within like 5 minutes. So this is actually what motivates most of the work here. So the conclusion is that the data generated from our sensors today, in the near future, will outpace all the methods to process that efficiently using the current approaches. And what we can do is we reformulate this image processing task as graph-based problem, and then we can take advantage of the new linear solvers and the new graph technology. So the last point is actually quite important, that there's actually lots of room for R&D for image processing using graph solvers. So one advantage that images and signals have is that their graphs are really, the set of graphs, right, are really small there. They're either a grid, a cube, or some, like the one you saw in hyperlapse, is a line graph with some small fully connected component. So what I'm trying to say is that maybe if we cannot solve the general class of problem, let's just try to solve this small graph, this small set, and we get very good speed up, and we have some nice tools to use.
But the cube is very different from the grid. What? The cube is very different from the grid.
The cube?
Yeah. Because you know, it's much more general. Because the grid is planar, it has all this nice property.
Yeah.
It stays planar.
No, but the point is like it's like there's only like 3 or 4 graphs to solve.
Oh yeah, I agree.
So we can maybe even hardwire all the sparsifiers and get a new tool to sell. Okay, okay, that's all for my talk.
I still don't see why you wouldn't compare this to the performance of an optimization algorithm. So if you get an optimal solution and yours is good enough or maybe even better quality in terms of whatever you want to achieve, then the optimal solution, that just means that the objective function that you set up in the first place is not the right one. But if you have the right objective function and you want to solve it, why not run it in the same amount of time as the optimization algorithm and compare the results? I just don't see how you can report on success without comparing it to an algorithm that is very efficient. In practice, it solved problems on 1/3 of a billion edges in the graph, and it solved it in under a minute, and that was a few years ago. So today it can do it a lot more efficiently.
No, but
And so
my question would be, in your framework, how many problems can you like compose them together? It's like, is it possible to write like denoising, segmentation, and a bunch of problems together in one major system?
I'm not sure what you mean, but the algorithm works for any Markov random field that has the 2 terms that you were showing.
No, but that was only one of the graph, one of the image processing problem I wanted to solve, right? So you can think of it as like, yes, I have an MRF, but this MRF I still want to find some, like I want to constrain like maybe half of it with some values, and I still want to do some composition of a bunch of tasks on it. So then once you get into that scenario, then I'm not sure how your MRF will look like, and we really do not really know how, if the formulation still holds.
Well,
I agree with you that if we do.
So the Mumford Shah, for instance, people never solve it as is anyway. If you look at the literature, nobody solves it.
Sorry, what
they do, Mumford Shah.
Yeah, Mumford Shah, yeah.
Showed initially.
Yeah.
So they solve essentially some approximations.
Yeah.
Always the approximations end up looking like Markov random fields, ultimately. And that one they solve with techniques of similar flavor to what you're showing, not necessarily using linear solvers, but iterative techniques that are not exact, and hopefully they converge to the optimal solutions. But if you have, so once you do the transformation and you come up with a formulation, that is fitting into the framework of Markov random field. And Markov random field is very general. The functions that you showed on that slide were particular functions, where for deviation it was quadratic, and for the separation it was absolute value. This is just no problem at all.
No, I agree with you. I agree with you that.
But if you want other ones, I have a paper in which I gave a whole list of those that are used in the literature, and how to discretize them, and how people have discretized them, and how you can solve them more efficiently in the Markov random field setup. So it's not, I don't understand, does your system automatically formulate the problem? No, it doesn't. So what exactly is the advantage?
But the simplest of all problems is, given a graph in 2 points S and T, find me a small edge cut. That problem, supposedly, there's famous papers coming out of here and MIT and these others which get near linear times.
No, I agree with that.
But let me just finish my sentence. So if for some reason you'd already solved that problem, you should go back and complain to them and don't worry about us. Because they're getting major credits for being able to do the ST cut problem.
I understand what you're saying.
And you're linear time. And if you're claiming you already have an optimal algorithm for it, why mess around talking to us? You should go tell them that they should pull their paper. I don't understand.
It's not exactly relevant to the issue.
Oh no, because that's a special case of what all he's doing. So under the hood is the ST cut problem.
I asked earlier if the idea is to solve this particular formulation, because this particular formulation is a cut procedure.
No.
And therefore, whatever applies to cut with linear systems applies, and that's fine, that's totally fine.
Yeah.
But I asked if this is the contribution, and you told me no, that this is something more general than that.
Yeah.
So
the contribution is like, if you look at this whole series of work by Microsoft, right? Like this set of work, this set of work, and the hyperlapse, right? They all have different graph problems. They all have, like, maybe every single of the technology, they have a different graph problem they set up. And they use a different solver for every problem they solve. But what I'm saying is that a lot of this problem, if you think hard about it, right, you can actually rewrite them into one single linear system, and that's it.
I think definitely, at least there is a sense in which, you know, one nice motivation for this is you write down the problem, which is a min-cut problem, and then you know that you can solve. Now we know that you can solve min-cuts using electrical flows.
Right.
Right. So this is at least a motivation for why one might even consider electrical flows in this framework.
Right.
Right. You have a slide which does this Laplacian relaxation, but in some sense, I mean, this is this came out of thin air. And at least one thing is that it you know, I mean, a very clear motivation is that you're trying to solve a min-cut problem, and you know, and now we know how to solve min-cuts using electrical flows.
Right. Yeah, that's essentially the spirit, although it's not exactly min-cut, it's parametric min-cut. It's not clear to me how the linear solver does parametric min-cut, but that would be fine. I mean, to study how it works, that's totally good, but now you're not doing any comparison to these things, so I don't know why this is good performance, what you're presenting here. I don't know in what sense it's approximate, and I don't know in what sense it's fast. I mean, you can do nothing, and then you have the fastest algorithm possible, which is approximate in some sense also.
It can't be, because otherwise all these poor kids that did this other paper, they're going to have to quit, because, it would already been done. So, you have to go back and say...
I have checked her paper. Her paper is about reducing to min-ST cut. Her paper is reducing the Mumford random field to ST couple.
Parametric.
Yeah.
Parametric.
Yeah, so two problems is different.
Oh,
he assumed we can solve ST cut then.
ST cut problem?
Yeah.
And in that sense, it's optimal.
It shows that it's parametric, and this is for this particular objective function.
No, but this objective function is only like one objective function of like the hundreds of those that we try to compose.
For the other ones, it's a little bit more elaborate. It depends. If the separation function, you keep it as absolute value. Any convex function is still parametric minimum cut. And the running time is the fastest possible in the sense that it generalizes minimum cut, and it generalizes spanning zero of convex functions, and the running time is exactly the sum of these two terms. And in practice, I implemented it. It is exactly the same objective function that you showed, and I was able to address problems, well, the type of problems that I got had up to 16.9 million pixels. And I was able to do it very fast. So in practice, it works well. So I'm now wondering, and there is also, I showed how other type of TV problems can be cast as Markov random fields and therefore solved, I don't know if to say more efficiently because no one has actually solved it exactly before, but now you're proposing a bunch of things that are fine, but now in what sense is this better? Not clear to me.
Okay, I'm looking for collaborators to work this. Maybe we can take this offline and try to figure out how we can work together. Okay, any other questions?
I have a quick question about you combine the denoising process and segmentation.
Yeah.
So can you apply your idea on if the image is blurred?
Sorry,
I mean the image is blurred, not the denoising.
It's blurred?
Then can you do the deblurring and segmentation at the same time?
Yeah, you mean a block, right?
Yeah, blurred.
Yeah, so we did it blurred. Oh, then you can solve the deconvolution problem as well.
Yeah, so you combine the both things.
I think you can. If you already know the deconvolution function, which is your inverse of your transfer function, you should be able to deconvolve n segments as you go. Because the convolution is equivalent to some zero order transform on your vertices only.
So I have one question. I mean, here you, as you said, that you're concerned, say, with a grid graph.
Yeah.
But as far as I understand, you're using these general purpose solvers to do this stuff. Yes, I don't.
No, for grid, I actually use a CMG.
Okay.
Yeah.
So I'm just.
But I'm saying that in the industry, no one actually uses CMG or any other specifier.
So in your undergraduate thesis, you also used non-local methods, right? Where you tied together pixels that were further apart, so you overlaid a graph. But you're no longer using those methods? Or they didn't work, that was just done?
It didn't work.
Because there was another talk here by you, and she was adding the complete graph over the top, and she found that very useful. She was doing variants of that, right?
Yeah.
So, I mean, and I think, Stella, you, I think, was adding an arbitrary random, graph.
I think a lot of this problem is actually with the solver, not with the formula.
So the only reason to say that is because then, as soon as you've added a random graph to your grid graph, it's no longer a grid, and then you have to figure out what you're going to do.
Right.
I mean, I'm just curious. I mean, I talk to people who are doing things in nanotechnology simulation where they have a grid, but then because of some quantum effects, they also have to contract some subsets of the nodes. And I'm just sort of wondering at which point one expects that sort of general purpose solvers.
So my experience is that the general purpose solvers are useful for doing experimentation, like trying to figure out what is the general flow of the algorithm. But once you're done, you have a good idea of what you want, right? Then people tend to just switch over to dedicated solvers where they design specifically for their class of problems. So in our case, right, we actually have, for example, when trying to solve the very large satellite image, we do the grids for experimentation. Then after that, we run some sort of like nested dissection to solve the entire grid.